And then people said, oh, I'd like to have an example. Can we have some real industrial application instead of this abstract physics nonsense? Can we please implement a kernel? How do you use this in practice? How do we do this correctly? I don't understand this. How do you choose between different, how does this, can we please do an example? Please, okay, so today we'll do an entire lecture, one example, okay? In detail. And I will see how much you like that, okay? And I have 90 minutes now. By now, I only have 85 minutes to do this. So I am going to do my closest approximation to an industry example I can do in 85 minutes. Because I can't build a viable product that you can sell on the market in 85 minutes. So I'm going to do this data set. Yes, it's one-dimensional, but it's very interesting. So who has seen this curve before? What? Like 6 people. Okay, so this is one of the most famous data sets collected in all of science. It's the amount of CO2 content in the atmosphere measured since 1958 on the summit of the volcano Mauna Loa in Hawaii by the North American Observatory for the Atmosphere, something. It's like the National Observatory for Atmosphere, whatever, like the American Agency for Collecting Weather and Climate Data. And so what you can see here is time on the x-axis in years. These are the actual years. And on the y-axis, parts per million CO2 in the atmosphere. It's a very simple measurement. It's been working since 1958. It has measurement error of below 1 part per million, so it's very precise. And what it shows is basically the best one-dimensional reductionist perspective on what humans have been doing to the atmosphere of the planet. And the question, of course, is what happens here? So we are now somewhere here. What happens next? How does this continue into the future? Maybe useful to know is that around 500 ppm, there's clear scientific evidence that humans just become stupid around that amount of CO2 in the atmosphere. Our bodies are just much worse at getting oxygen in then. So maybe for those of you who didn't have a physics background, the atmosphere is mostly oxygen and nitrogen, so 68% nitrogen, 21% oxygen. And then these are tiny amounts. And our bodies, because of these relative proportions, don't really have problems getting oxygen into our erythrocytes. We have problems getting rid of the CO2 because the CO2 binds much better to them than the oxygen. And because of these partial pressures, the main problem is actually CO2. So this isn't even just so much about climate change. It's also about whether we just become idiots at some point if we keep doing like this. So how do we do regression on such a problem? This is the perfect example of one of our regression problems. It's a one-dimensional problem. The output is real valued, and the input is one-dimensional real valued. So I'm going to build a model for this purpose. And here is the code for this that we're going to use today. I'm actually going to run it in real time. Let's hope that beat up Jupyter Hub doesn't die on me. So what we do at the beginning, of course, we are setting up our environment, loading all this stuff that I keep using all the time. In particular, I'm going to be loading our Gaussian class that we've built over the last few lectures, and I will actually keep using this. And this also contains our Gaussian processes. Then I'm going to actually load the true data from today. I tried this again this morning. You see the most recent data point is from yesterday. The reason for this is that I'm loading the weekly data set. This has been collected since 1958. That's going to give us something like 800 data points we can work with. It's sufficient temporal resolution, 52 data points per year, to give us a perspective of what's happening. There's also a daily data set you can try yourself, but then we get 7 times more data points. Everything gets very large, and we'll have to start thinking about numerical computation, which is what I don't want to do today. So, by the way, the first person who started collecting this data was called David Keeling. He's still in the CSV file, and this is why this is called the Keeling curve. So here's the actual measurements. They come in here with years and weeks and dates, and these are the actual numbers. These are the Y points that come out, and there's a bunch of other data as well. And I'm going to, this is not good. Okay, can I move my mouse over here? No. And I'm going to store this in a CSV file, also for your purposes, because I was a bit worried that NOAA might get out of funding any day now. So I kind of have a backup data set here to work with. But this morning, it still works. And now what we can do is we can first make a plot. We'll get the usual error message. So I'll run the cell twice, then the error goes away. And this is the data that we're looking at. OK? So here is a curve. And one interesting thing, you may notice that this curve is sort of smooth on some time scales, and it also is rough on some other time scales. By the way, what's happening here? Why do we get these ups and downs? Who has an idea?
It's the yearly distribution because in the northern hemisphere there's such much forest.
Yes, so it's seasonal processes. The atmosphere doesn't really mix all that well between the northern and southern hemispheres because of the tropical cycles in between. And what we're seeing here is like the plants in the northern hemisphere not absorbing as much CO2 in the winter as they do in the summer. And so we get like ups and downs over the year. And they have a period of exactly 1 year. So the very first thing we could do, the naive thing maybe, is to say, can we find a straight line that goes through this data set? Yeah, that's your linear regression. So by now, we know that we can think about linear regression also as a kernel setup. Actually, can you read this? Do I have to increase the font size at the back? Yes. Like this? Can you read the equations now? Just about? Everyone else in the back as well? No? I'll try and make it even bigger. At some point, it gets harder to go through the code, but now? OK, good. So you'll remember that we introduced linear regression with this simple setup of saying, let's build a function phi of x transpose w is w1 times x plus w0, right? Intercept plus gain. And this is a sort of a parametric model. But if you think of the covariance between these function values, we could use a standard Gaussian prior that says our P of W is Gaussian, or W with mean 0 and covariance 1. Then the covariance between function values, which is which has covariance phi transpose sigma phi, will become x1, x2, x1 transpose x2 plus 1 plus a constant. And that's actually a kernel, right? You can think of this as a regression model, as a Gaussian process regression model that uses a kernel. It's just a degenerate kernel in the sense that this kernel always has rank 2, I guess, right? Or 1, well, 1 or 2, depending on how we think about it, but finite for sure. So let's implement this. So I've implemented this little kernel, a function that takes 2 inputs and returns a scale times the inner product between them plus a constant. And I've also implemented a zero mean function. That's a function that just returns zeros if you give it x, zeros of the right shape. And now I can do Gaussian process regression. I can say, let's build a Gaussian process prior that uses this zero mean function, and it uses this linear kernel where we set the constant to 100, which gets squared. By the way, what does that 100 mean? We talked about this last Thursday. So today, these numbers are going to be important because we're talking about physical quantities. We have years on the x-axis and parts per million on the y-axis. And we want these numbers to mean something. We want to predict what the parts per million are going to be in 5 years' time. Right? So if the number is 5 or 50 or 350, those mean different things. So our 100 is the scale going in. If you would draw from this prior distribution, you would get something like around 0, some distribution that looks like this. Draws from this distribution would be linear functions. And the width of this here would be 100. That's where the 100 comes in. And the variance in their gains is also going to be 100. Now, we condition this Gaussian process prior on data By now, we have built all these cool tools to do this. So I'm going to save us the time of going through how this linear algebra works again. This is the advantage of abstraction in computer science, one of maybe the most powerful concept of computer science, that we can wrap really complicated mathematical ideas behind such simple pieces of code, right? So now, from now on, we're not going to talk anymore about what it means to condition on a Gaussian process on data. We'll just call our little function. And then we'll plot both the data and the posterior distribution. And I'll keep doing this over and over again, so let's maybe time to think about what this does. Okay, so if I make this plot, takes a bit of time because Jupyter has to wake up, and here is our prediction. So you actually see here a full Gaussian distribution. It's not just a mean, a straight line, but this posterior is so concentrated because there's so much data, 800 different data points, that this model becomes very confident about what the best linear fit to this data set is. So, okay, your first reaction to this, what do you think? Yeah. Yes? Shouldn't the model be more uncertain? Yeah. So this is maybe an interesting first observation. Something that I've maybe pointed out not quite often enough, but I'm going to point it out more frequently, is that the posterior covariance of a Gaussian model, which you've now written down several times and thought about and also implemented yourself, does not depend on the y's in the data. Right? So the posterior covariance is just prior covariance minus this sure complement multiplied from the left and the right with features of x, but there's no y in this equation that gives the posterior covariance, which means this model has no way of figuring out that it's a bad fit so far. We'll need to deal with that, right? And therefore, it just becomes confident because it has a lot of data. What this says is, if you give me 800 points from a straight line, I bloody well know what that straight line is, right? Because I basically need 2 noise-free points to know what a straight line is. If you give me 800, I'm going to be quite confident, even if you have a little bit of measurement noise. And the fact that this is a bad fit is not something we can deal with within this Gaussian framework. But we'll deal with it today by fitting the parameters of this model. Now, here is this sort of mental dichotomy that you can go through. If you're thinking probabilistically, you already have sort of the Bayesian viewpoint. Your mind is going, but this is bad. Right? This is not a good fit, and it's still certain about it. We shouldn't have this. On the other hand, think about how often you've seen people draw a straight line through data sets like this. Right? This is completely common. This happens all the time. In the media, you can see predictions like this all the time. Maybe they're not quite like as brutally visualized as this, but it happens all the time. And then people just don't draw any uncertainties, posterior uncertainties, and then it's somehow fine, right? If you just don't talk about uncertainty, then it's okay to make a bad fit. Of course it's not, but the probabilistic perspective forces you to think about these objects. It returns this Gaussian distribution, and then it's this natural reaction to go, but that's bad. We shouldn't be using this. So let's try and fix this. And this is, for me, actually, maybe one of the most important aspects of probabilistic thinking, is that it forces you to think about the degrees of freedom of your model and whether you trust these predictions, because it always gives you back these uncertainty estimates. OK, so this is clearly not a good solution. Let's do something smarter. And thankfully, we've already found lots of smarter opportunities to build better models. So the next thing we're going to try is a little bit less knee-jerky, but still a relatively easy approach, which is to say, by now I have this cool tool called Gaussian process regression. Let me use a Gaussian process, a proper Gaussian process, not a parametric one that basically just wraps around a 2-parameter model, but actually uses an infinite dimensional distribution with infinitely many features and a countably infinite number of degrees of freedom. So I'm going to use one of these so-called stationary kernels that I told you about on Thursday. I could pick actually pretty much any one of these kernels I introduced. For example, I could take one member of the Matern family. I could take this Gaussian kernel, the RBF or square exponential kernel, or I could use, just to mix things up a little bit, this rational quadratic kernel, which I introduced on Thursday, which is a generalization, a scale mixture over these square exponential kernels. If that confuses you, I invite you to come back to this code later and just replace this line that follows here with this kernel with your favorite simpler kernel, your Gaussian kernel. So this kernel is a function that takes two inputs A and B, computes their square distance, divides by a bunch of constants, and then computes 1 over 1 plus this distance to the alpha, where alpha is a number larger than 0, and scales by a parameter. By now, if you followed on Thursday, you probably know what this parameter does. It scales the prior up and down in its output width. This parameter L scales the length scale so that our time window has a meaningful measure of length. And this alpha is a dimensionless quantity that scales the scale mixture. If alpha is close to 0, the function has a lot of different length scales. If alpha goes towards infinity, we asymptotically get back the Gaussian kernel. So I've implemented this kernel here. It's this basically one line broken into 4 in Python. It takes an input A and B, and then it computes exactly this equation. And admittedly, this equation is easier to read here than in Python, but yeah. So the other thing I'm going to do is I'm going to create a constant mean function, not a zero mean function, but I'm going to just build a function that when probed at x returns the data set mean. This is the maybe more explicit approach to correcting the data for the mean, right? So instead of subtracting the data mean, I'm going to like pre-compute it and then keep it around so that it gets subtracted at every single step. This allows me to build a new Gaussian process model that's maybe a little bit smarter. It has a constant prior mean and this rational quadratic kernel. Then I can condition, let's do this. Remember from last Thursday that all the lines up until here cost nearly nothing, and then this last line is the thing that actually does the computation. And now I make another plot. Takes a bit of time, and here is the plot. Okay, so now we have a maybe more powerful model. So what do you think of this output? Yes, please.
It looks well for the data points, but it doesn't generalize.
Yes. So this is maybe a real machine learning model. So what it does is it's designed to go through data points. It's designed to interpolate, right? This is a kind of model that is very good at going through all the data points. So if we are inside of the data set, you could say on distribution or in distribution, then this model is arguably quite good, right? I could probe it at any point in between 1960 and 2020, and I'll get a very precise measurement of what the CO2 content was at any particular point in time. But if I go to the left and right, if I extrapolate, if I go out of distribution, then this model has the property that asymptotically it goes back to the prior mean. This is a so-called stationary model. And sometimes in machine learning we like this because it means that you can't go really wrong, right? You just go back to 0. But if you think about this as a scientific prediction, it's pretty much useless. This is a typical setting where we want to extrapolate. I mean, the entire question is about what happens next. And for this purpose, we cannot use this model at all. It's completely bad. Right? OK, so what can we do to address this? I'm going to save us some time. Actually, maybe, OK, I'll give you 30 seconds to think about this. It has to do with what we did last Thursday, these closure properties of kernels. So I said on Thursday that you can do various things to build new kernels from old. You can scale their output to make them wider as a distribution. You can linearly or non-linearly transform their inputs to give a different meaning to the input domain. Or you can multiply two kernels or add two kernels together. I said that adding is like an OR relationship, while multiplying is like an AND relationship. And we can use these latter two properties to build new kernels that maybe address our problem that we have here. Because let's think about what happens with this data here. So by the way, this is a very important point. We see this problem because we can look at the data. Right? That's why I've actually picked a one-dimensional data set, because then this is very obvious. in your real-life work, you may not always be as lucky that you can work with a one-dimensional data set, but then you will still typically have to find some way of looking at your data in a lower dimensional fashion. If you want to hear more about that, I invite you to come to the data literacy class next winter term. But this kind of problem, right, you'll only notice if you actually look at your data. If you're the kind of strawman machine learning engineer that just says, I have this tool set, let me just use it, here's my prediction, you will hardly ever notice that this is what's happening in your model. So, okay, let's think about what we can do. We look at this data, and what we see visually is that the problem with this data set is that it has different length scales. It has this periodic component that happens on the time scale of 1 year, up and down, up and down, up and down, but only a little bit, right? In Y, this is a very minor perturbation. And then it has this long length scale that over many years, actually over decades, it keeps rising. So we need a description that says, on the one hand, on short time scales, the function wiggles a little bit, but on long time scales, it moves a lot. And we can model this by a sum of two kernels. One kernel with a short length scale and a small output scale together, and another one with a long length scale, so things can only move on long length scales, but then a wide output scale. There's a question. Say again? Why not multiplication? Okay, perfect question. So multiplication is like an OR relationship. So if we would multiply these two kernels, actually, okay, let's keep this question in mind for a second. I'm going to show you the output of the sum, and then let's think together what would happen if we would do a times. Okay? Maybe that's even better. Thanks a lot for this question. This is great. So what I'm going to do is I'm going to write a long-term trend kernel. And for this, I could also use the rational quadratic kernel again, but just for fun, I'm going to use a square exponential kernel, a radial basis function kernel, a Gaussian kernel, the most default kernel people tend to use for kernel regression. So it's a kernel that takes two inputs, takes their square distance, divides by the length scale, and that length scale will be something like 10 years for us, or maybe even 100 years, and multiplies by an output scale. And that output scale we can sort of read off, right? It's going to be something like 20, 40, 80 parts per million. Right? So we want to cover sort of this range of the data set. Maybe even 100 could work, something large. And then am I doing this with just a long-term trend for now? Okay, so let's just do a long-term trend first. So this is just our long-term prediction. Here we go. Yeah, so if we only use the long-term prediction, now we get, at least the output scale is fine, right? But in between, along the data set, we sort of have to average over these periodic components. We can't model them with this long length scale. And then we get also these nasty spikes at the outputs. This comes from over-constraining this model to learn a straight function that goes through all of these periodic components. This is sometimes called the Runge phenomenon. After, maybe some of you have heard of Runge-Kutta methods. This was sort of early days of interpolation. They also had this problem, and they had to think a lot about what to do about this. There was a lot of mathematical theory to fix this. So what we're going to do is we're going to build a sum now, a sum of two terms. So we'll build a new kernel, a wrapper around our kernels, that takes in the inputs A and B, and then it uses a lot of different parameters to build two different kernels. A long-term trend kernel, our square exponential, with a length scale of, actually, I'm going to set the length scale to, sorry, where is it? The length scale to 50 years. So I'm going to say that this smooth change has to happen over 50 years. And the output of that kernel will scale on 100 parts per million. And then there's going to be this short-term component, which moves on a length scale of 1 year. But it only affects about a contribution of 5 parts per million up and down. So that's a small component. And those two together can then interact through a plus, because our implementation says, return please the plus of these two terms. And we'll use the prior, we'll condition, and it runs, and our model now produces this output. So what you can see now is that this function interpolates nicely within the data. And then it extrapolates on the long-term trend with a kind of a more meaningful uncertainty. And what you see here, by the way, in the background is I'm also plotting draws from the prior in black so that you can sort of get a feeling for what kind of model assumptions this model makes. Now, actually, so coming back to your question, I would still like to defer your question for one more kernel to fix, but then we'll get to it. But maybe just to point out, if you would actually try this for yourself later on, go through this code and change the plus to a times for this particular plot. My personal prediction is it's going to be hard to see the differences between these two. But in the next step we'll do here below, the difference will be much more stark. And then you'll know it's going to be easier to see the difference between plus and times. By the way, your homework exercise this week is going to be building on this data set. So maybe one thing you see, and that's already happening in your head as you're following along. By the way, what's the speed like? Can you not vigorously if the speed is okay, and shake your head if it's too fast? Maybe that wasn't a good question. Okay, the speed is good. Good. So maybe one thing that can go on in your head because you have 3 cycles is, oh man, Hennig is now introducing this stuff here, and he's making all these wild assumptions, right? 152, whatever. Why should I believe any of these numbers? They just fall from the sky, right? So this is a problem with scientific models, that to build an expressive description of the data set, we tend to have to introduce new, sometimes one of my collaborators once called them Stradivarius factors or fiddle factors, right? So you're just putting in some numbers. You don't really know why you use them, but you notice that they actually mean something, right? So I'm not setting them completely freely. I'm setting them to something that makes sense. They have units of measure. So the unit of this is years, right? 100 years, not 100 pixels, 100 years. The unit of measure of this is also years. Changes over 5 years, over 100 years, on 50 parts per million. That's the unit of the y-axis. And the length scale, sorry, that was wrong. These two have units parts per million. This has unit years. This has also unit years. And alpha is a dimensionless constant because we are raising our kernel to that power. So I'm not setting these numbers at random because I know what they mean. But admittedly, these are set to awfully round values, right? 50, 100, not really trusting those. Okay, so but maybe one way of dealing with this is to look at these prior samples and say, do these prior samples look anything like my data? Right? Do they kind of move on the right scales? And in some ways, they now do because they cover the right range. So they lie in the right region, they move on the right scales. But also, if I would give you this blue data set that you see in the background and these black lines and ask you which one is the real data set, you would all be saying, well, it's obvious, right? So clearly, this looks very different from the samples. So this is not yet a good model. Okay, so one way to address this, maybe the most salient feature of this data set, that's what's not working well yet, is that we know that this data set has these periodic components, and they are literally periodic, right? They're seasonal forcings that are not just random draws from some Gaussian process that creates functions that wiggle around. They are ups and downs with a period of exactly 1 year, and they move up and down on pretty much the same range. So we need a model for periodic components. Now, if I were using a parametric description of the regression problem, then maybe some of you could come up with some features that move periodically, right? What would be your proposal? What kind of features would we use? Trigonomic functions, yeah, a sine and a cosine, exactly, right? So this is a good first step. A problem with this sine-cosine approach is that we're then going to learn a periodic function that has to be perfectly periodic and be a constant multiple of the sine and maybe a cosine, right? So it's basically 2 numbers that we're fitting. So then we only have 2 components to fit something that probably isn't actually a sine curve, because it models, as you pointed out, this quite complicated biological process of trees absorbing more or less CO2. So the curve is not going to look like a sine, right? I mean, the seasons actually, I mean, the sun around the Earth, that's literally a sine, to very, very good approximation. But what the trees do in the spring and the fall and so on is a bit more complicated. So we'll need a slightly more expressive model. And here I'm going to ask you to trust me to go through something relatively quickly. It turns out that there are some really cool kernels for periodic functions that can model functions that within one period have general degrees of freedom. So they are smoothly moving, and not just with 1 degree of freedom or 2, but an actually infinite degree of freedom, but still move periodically. And the trick to do this, I invite you if you want to know more, is to read this original paper by David Mackay from 1998, where he's literally approaching exactly this problem, right? I want to do regression on a periodic function, and the way to do this, I mean, you can read it off basically here, is you take, you embed the unit circle within a Euclidean plane. So the unit circle is a Riemannian manifold embedded within this two-dimensional plane, and then you read off the parameters, one parameterization of the circle in this plane, embedded in this square exponential kernel, and you'll get this kernel, which is a model for functions that are periodic, but can move relatively freely with length scale L on this periodic component. And I've implemented this kernel here. So what is this? It's literally a function of two inputs, a minus b squared times divided by 2. And then we take the sine squared of this. It turns out that that's still a kernel. You can find the proof in David's paper. You can read it up. And here the important thing is we could multiply this expression with a period, right, with a multiple of 2 pi, to decide what the periodicity of our function is. But actually, we don't need to do that because we know what the periodicity is. It's 1 year. And because our data comes in units of year, I just multiply by 1. That saves us 1 Stradivarius factor. Cool. OK, so let's do that. We'll implement our Gaussian process with this periodic kernel. And now, maybe first to understand what kind of functions this process produces, I've made a plot. I've put away our data for a moment and just made a plot of draws from this process. So on the left, you see 2 draws from this process. Actually, maybe I should only plot 1 because it's a bit too confusing. So one such function might look like this. And you see that it's a perfectly periodic function, but it doesn't look like a sine. It's a bit more complicated. And it doesn't, maybe looks a bit boring. If I wanted to make it less boring, I could set the length scale to, yeah, well, okay, I mean, where's this length scale? Maybe let's set that to 0.2. Dangerous thing to fiddle about with my code. Yeah, okay, now you see that these curves are now, they're still perfectly periodic, but they have more degrees of freedom. They can have dips and bumps and so on. Now, our curve probably won't look as complicated as this because, I mean, we know that it's, seasons up and down. It's not going to have these weird kinks. So maybe let's go back to 1.0. And now the only thing is that I don't actually believe necessarily that this would be like maybe a bit of a wild scientific assumption to say the seasons have not shifted at all over the last 50 years. They might have shifted actually. So to model this, I'm going to use the product idea. And I'm going to say I'm going to take this kernel that makes these perfectly periodic functions, and I'm going to multiply it with another square exponential kernel, so another Gaussian kernel with a length scale that is longer than 1 year, maybe 10 years or 50 or 100 years, that says the periodicity of these functions decouples over length scales of maybe 10, 50, or 100 years. So that if you go 100 years into the future to a particular date, to like the, what do we have today, the 13th of May, then the temperature or the CO2 content on the 13th of May this year doesn't have to be exactly the same periodic shift as 50 years ago, but it can drift a little bit over time. Only within this periodic component, of course, right? The rest is, can still change over longer length scales. So we can use this to build a model, that's maybe where we do our plus and times idea, that contains our long-term trend from before, But now for the short-term trend, instead of this rational quadratic term that just says it's just some function that moves on a short time scale, I'm going to use this periodic kernel that uses a period of 1 year with a length scale of 1 and an output scale of 1 part per million. And actually, here's where I set the parameters. So I'm going to set the, OK, let's look at that. So I'm going to say over the long term, the function moves on a scale of 100 parts per million. In the periodic component moves on a scale of 5 parts per million. The length scale of the long term is 50 years. So things move on scales of 50 years. And the periodic component has a length scale of 1 year. What that means is not that the function is periodic on 1 year. That's already hard-coded in our kernel. It means that within over the periods of 1, we expect our functions to be relatively smooth within 1 year. We expect something that goes down and comes back up again. It doesn't have to be a sine or a cosine, but we don't expect a function that has a lot of wiggles within 1 year. Okay, and then I'll build this prior, I condition it on the data. Notice how nice this is, that we can just call condition. We don't have to think about it anymore. And now we get a model where in the back you see in black the prior draws, prior samples. And after conditioning, we get this red distribution. So now we have arguably a slightly smarter kernel, right? A model that produces data that you could still probably pick out the original data, maybe, but the regressor now extrapolates in a much more powerful way. So you can actually barely see where the data ends, right? I mean, it ends exactly today, 2025, around here. And you can see that this actually extrapolates quite well into the future. We see our seasonal components coming up and down on the right scale, roughly the right scale. And then we see this long-term trend that produces this bend shape here. So can we trust this bend? I mean, that's a very promising prediction. I say, ooh, cool, it'll come back down, right? Nice. So why does this happen? It happens because I've set the length scale to 50 years. And that means that this regression model will return to its prior mean over a length scale of 1 to 2 multiples of 50 years. Right? This has nothing to do with scientific prediction. It's just a model property. So next takeaway is when we build such models, we have to be very careful about which of its behaviors actually come from our prior assumptions and which of them come from the data. By the way, now let's just see what happens if I replace the plus here with a times, oops, not an and, but a times. And I just run the same thing again, so that's the answer to your question. Oh. Right, so that's your why we don't want a product. So intuitively, what happens here is that function values are now only similar if they are similar under both the periodic component and the long-term component. And that means because the short-term component dominates, they are only similar on a short time scale. And then afterwards, they just vary really wildly. They vary on the scale of the large component, but along length scales of the short component. So or is not the right relationship here. We want a plus. OK. Let me see how far I can get before the break. Now, this was the first step of our process. By the way, let me show you one slide that I forgot to show you to explain what we're actually doing here. So what we're doing here is we're using the properties of like the closure properties of kernels to build an expressive language that describes everything as much as we can possibly in code in terms of prior knowledge about our data. And I keep using this plus structure for these purposes. One way to think about this plus property is to say, you can imagine if you have a plus in your kernel model, if you're adding 2 kernels, then one way to think about the modeling assumption inherent in this process is, okay, so one way to think about what happens when you have a plus in your kernel models is that there are actually 2 functions being modeled here. They each have their own kernel. And what we observe is their sum. And by the properties of Gaussians, right, if you have two different functions that independently move according to two different kernel models, then their sum has a distribution that is Gaussian, because the summing is a linear map, where the mean function is the sum of the two mean functions, and the covariance function is the sum of these two covariance functions. So there is actually underneath this model a hidden assumption that there are actually two functions being added here. We just don't see it yet. Right? We can't currently see these two separate functions. But actually, if you have the time towards the end of today's lecture, I'm going to try and tease out the individual temporal components of this. But now, though, it's time to build an actual model for our kernel regressor. We now have all the contributions that we need. We have a way to set up a long-term trend. We have a way to set up periodic components and maybe various other terms as well. So what I'm going to do is I'm actually going to build a pretty expressive model, which, by the way, I forgot to mention this at the beginning. It was briefly on the slides. The idea for this model I'm taking from Carl Rasmussen, who built this original model for his Gaussian processes for machine learning book. Remember that was written around 2001 or 2 or so? Maybe it was published. No, sorry, it was published 2007, I think. So this goes back quite a while already. This data set has been interesting for decades. And I'm actually going to use pretty much his model setup, which is to say, we're going to assume, first of all, that there is a long-term trend in our data set. That is the thing we actually maybe are most interested in, but we need to tease out all the other effects and model them by different components. Then I'm going to set up this periodic decaying kernel that says there is a period 1 small perturbation that models the seasonal trend, and that seasonal trend changes on very long time scales slowly because the seasons might shift. Thirdly, I'm going to assume that there is some medium-term things going on as well, just for the sake of it. So let's say something like weather patterns, right? There are some years that are a little bit warmer, a little bit colder, more winds, less wind, that move around the CO2 a bit more. Or it might also have something to do with what we do with the atmosphere. Maybe it's something like GDP growth or wars and pandemics coming through, changing our output. So this I'm going to model with another actually rational quadratic term. So you've seen this kernel already, which will have a length scale that is between 50 and 1 year, and an output scale that's also a bit more medium term. And then finally, there is going to be some noise term, which doesn't actually describe measurement noise, because measurement noise is quite well understood. It's very small for this data set, but it maybe describes, let's say, very local phenomena that happen around Mauna Loa. Like there's just, some thunderstorm coming through for a week, and then like CO2 components, CO2 concentrations go up and down a bit. So this is going to move on a length scale of something like 1/10 of a year, right? So very, very quickly, locally, on length scales of weeks. Okay, and that's going to be our entire model. So I'm going to write down our model and say our model consists of a kernel that takes in inputs x and y, and then all of these parameters that describe everything that's going on. The length scale, the output scales of all of these kernels, and they all have a physical interpretation. They have interpretation as input, as output scales, as input scales, as smoothness scales. Some of them have units of measure parts per million, some have units of measure years, and others have units of measure dimensionless, like the alpha in the rational quadratic. And they consist of a sum of the long term and the periodic, and the midterm and the noise. And I'm going to define the parameters for all of these. I'm going to say the length scale of the long-term trend is the output scale is 100 parts per million, moving on a 100 years time scale. The periodic component has 2 parts per million, and it changes the seasons shift on a length scale of 50 years, and so on and so on and so on. Yeah? And then I'm going to initialize, put them all into an array, basically. That's just storing them somewhere. Initialize a model with the constant mean of the data set that I've pre-computed and this complicated kernel, and then just do machine learning. That's now just one line. because we've abstracted it away. And that will give me a plot that looks like this. So in the back, you see draws from the prior. And here you see a prediction that now actually moves up quite a lot over here. And now we can ask, first of all, before we move on, how well we trust this model. One way to do that is to draw samples from the prior. So in this plot, I've made it a bit more extreme. I've just drawn 7 different functions from the prior and also plotted the true data somewhere in there. Can you tell where the data is? Raise your hand if you can see the data. Damn, it's not quite good enough yet, right? But you'll probably agree with me that this is a much better model than what we started out with. It's not straight lines. It's not things moving on randomly without periodicity. It looks pretty decent, right? But it's not perfect yet. So after the break, we have more work to do. And that work, spoiler alert, will be to fit the parameters of this model away from this hard choice that I've made to find descriptions that actually make this model as predictive as possible under the data. We'll do that after the break, so we'll take our customary 5 minutes now. So there were some great questions during the break. Let me see if I can quickly summarize some of the questions that came up. One was to point out, maybe that wasn't exactly the question, but I'm going to paraphrase a bit what might be a message to you, is when I make these plots, I'm arguing that we now have a model that is relatively good at describing what's going on. I'm encoding mechanistic knowledge about the problem by choosing the kernels. So maybe for those of you following from a more sort of statistical frequentist perspective, this may feel a bit dangerous to you. Because what I'm basically creating here is a bias. I'm building a biased model. And what I'm arguing is that this is good. Bias is good because it encodes salient scientific knowledge. So whenever we do that, of course, we're exposing ourselves to potential criticism. Someone who doesn't like, someone might say, this is woke, right? I've just built some model that encodes all this stupid knowledge that isn't true anyway because it's all fake, right? And then I'll have to defend myself. If I use linear regression, I don't. I can just say it was just a straight line. Well, there's not much assumption in there. But you've seen what the predictions look like. So we don't get away from this. We don't get away from arguing over prior assumptions if we want good models. And to maybe drive that point home, I invite you all, we're going to do this also later in the course, but maybe I shouldn't have mentioned this. I invite you all to try and build a regression model for this problem with a ReLU feed-forward perceptron, so with a black box machine learning model. Try to just write down your standard deep neural network, quote unquote, but don't spend too much time optimizing its nonlinearities, right? The moment you start fiddling with your model, you're also putting in prior assumptions. But let's just use a feed-forward perceptron with ReLU nonlinearities, 3 layers with, 2021, right? 2021 in Torch. You're going to get a stupid prediction, right? Because of the exact same problem. Maybe other terms people use to talk about this process that we're going through here at the moment is labels like interpretable machine learning or trustworthy machine learning or various other terms you may have heard about, right? They are sort of lofty, sometimes philosophical concepts that get talked about in very vague terms on the media. What they mean in code is this. Like being able to look at the prediction and the prior assumptions and say, what is in this model? What's going on? Okay, so now having said that, let's think about what we can do to make this model even better, to give it even more bias. What we're going to do is, we'll decide now that we fixed the model structure. This is the best I can do so far. Oh, by the way, that was another question. Someone asked, couldn't there be some other kernel out there that's even better? Why if you use this particular model? Well, here again, yes, maybe there is a better kernel out there. Maybe I could have spent 2 hours deriving one specific kernel for you today. And one way to do that would have been to sit down with a feature codebook and write down parametric components that I totally believe in, some kind of scientific model. That's the approach of classic physics, right? I could say there is force field number 1, which is one parameter of my model. I'll write that in. Field number 2, number 3, number 4, and so on. And you'll actually do a minor version of that in your homework. Because one thing you could do is you could say, maybe I know what the global GDP growth is. And GDP has maybe something to do with CO2 output. Let's put that in my model. This is what climate scientists do to some degree. Not completely, but this is sort of part of this idea of climate modeling, is that you create much more expressive, you measure more, right? Not just time as the input, but also causal variables. You measure, you put satellites into the atmosphere, into orbit, you measure plant surface growth and amount of algae in the ocean and all the other variables you could think of that you can sense remotely or locally, and then try to build parametric components in this model. We're not doing that here because it's a lecture on machine learning and we have 90 minutes time to do it. Right? I invite you to try and play around with this data as much as you like. It's your data set, it's open and public. Download it, save the CSV file before NOAA goes bankrupt, and play with it. Okay, so how do we fit the parameters of our frozen model that we've now designed? So for that, to do this, I'll now spend 15 minutes doing some math with you, because there is actually a generic framework for hyperparameter fitting from the Bayesian perspective. Before I show you that, maybe let me point out that there is also a frequentist way of fitting hyperparameters, and it's called splitting into a train and test set and doing some version of cross-validation. That's a totally okay approach. One thing I don't like about cross-validation is that when you have a data set that actually means something, like our data set here, then my question would be, where is the test set? Clearly, your choice of test set now actually has an effect on what's going to happen. I could, for example, say, I'm going to use the first 50 years as the test set, and then the last 20 years, the first 50 set as the train set, and then the last 20 years as the test set. That's potentially dangerous because it biases my model assumptions towards the past, and things that have happened more recently don't get used in, or actually maybe the other way around, right? I only use more recent data to check how good the fit is. I could also randomly distribute draws across the space, right? Just take 10% at random from the data set. That's also dangerous because it's a much easier task. So remember that we found some very easy models that could interpolate really well within the data set, but very badly outside. So you're suddenly faced with this problem of how to pick your train and test set. I'm not going to address this problem here. Ask Matthias Hein about it. He's the statistical machine learning guy. But I just want to point out that this problem is not trivial, right? It's not like this is the unique, correct, perfect answer and it has no criticisms, right? Instead, we're going to do let's say, the Bayesian thing. Let me just go back to where I was. Which is a generic framework that also applies to Gaussian process regression, but actually we're going to use it all over machine learning, which is called marginal likelihood optimization, or maximum likelihood, maximum type 2 likelihood, and it's based on the following kind of argument. So remember that we're using Bayes' theorem to do inference, but we're actually using it to do inference on something very specific. In our case, we're doing inference on our unknown function f, by conditioning on observations on data. Let's call them x and y. So these are our train inputs and train outputs. And that process involves multiplying a prior with a likelihood and dividing by the evidence, called Bayes' theorem, which we have implemented and cast into actual computations in our function called gp.condition, right? Gaussian.condition. But actually, this model also contains these parameters, these annoying extra choices that we had to make. Let's call them theta. That's a typical variable for parameters. So for us, it's all these different length scales, all this stuff that is in our code, right? All this, where is it? This whole thing, that's theta, right? All of these different choices. And they're still in this equation. They show up in the prior, maybe even in the likelihood. In our case, they're actually not in the likelihood because the likelihood model is just Gaussian noise with pretty much zero measurement error, so or negligible measurement error. So they're mostly just in the prior. But in the most general case, they could also be in the likelihood, right? The measurement noise could also be part of our model. And that means that this posterior distribution actually depends on our parameters theta, what it looks like. But interestingly, our parameters show up in these three different places. They show up in the prior, in the likelihood, and also in the evidence. And this term evidence is actually called evidence for a reason. Like the philosophical interpretation of the evidence is that it is the likelihood of the model. What we do to compute the evidence is we integrate out the unknown function under the prior. So what we're left with is a distribution for the data, the stuff we know, given the parameters, the stuff we don't know. So actually, this is another likelihood that we could put into Bayes' theorem again. We could come up with a prior for theta, multiply with this object down here with a prior, and divide by another evidence, which is the integral over this function against the prior p of theta d theta, and we would get a posterior over our parameters. The only problem is that this object down here will typically not have a nice form in terms of theta. It will not just be a Gaussian distribution that contains a linear map of theta. Remember what theta is for us? It's all these nasty things that go into the kernel, length scales, output. They're everywhere, right? So they are not just some set of linear numbers that get linearly mapped through the kernel. And therefore, it's going to be very hard to come up with a prior such that we know how to compute the posterior. It'll just be some algebraic mess. But we can still realize that the object we're looking at here is a likelihood. And in fact, we can ask what this likelihood specifically looks like for our Gaussian model. So yeah, okay, so this stuff up here is, maybe just reminding you of what's going on. If we have a Gaussian process prior, then the parameters might show up both in the mean and the kernel in the most general sense. If we have a parametric mean, they might show up linearly, but they don't have to, right? They could also just be somewhere nastily hidden in this nonlinear prior mean. And they will show up in various ways in our kernel. So for example, if you use the square exponential kernel that I've used in some of our code, then parameters might show up linearly in the variance. That's not even enough to do closed form inference because it's not in the mean. But they might show up in this very nonlinear fashion, right? With a square, in an exponential, in a fraction, within the kernel, in a very nasty way. So the evidence, the way that this theta shows up, we can actually nevertheless compute, though, as a function of theta by, again, using properties of Gaussian distributions. So you will remember that the product of two Gaussians, Gaussian PDFs, is another Gaussian PDF. We actually discussed this at length. We also implemented this function in our code. If you multiply a Gaussian that is a linear function of some parameters with another Gaussian that is a distribution over these parameters, you get out two Gaussians. The first one happens to be the posterior distribution, and the other one is the evidence. Why? Because notice that this is an expression that is a probability distribution over W, and this is an expression that doesn't contain W. So we can rearrange, actually. We can take this expression here. Actually, I could use my mouse. There you go. No, it's dead. Could use this term. And divide by it, and then I would have exactly Bayes' theorem, right? Prior times likelihood divided by the evidence is the posterior. So what does this evidence actually look like? Well, it's the probability distribution for y, the data, evaluated at the predictive mean, so the distribution for y, with the variance that is the predictive variance for y. That's this Gram matrix that shows up as an inverse in our posterior distribution. So our evidence is actually just this. It's the probability for the data under the prior model without having conditioned. Not the conditional distribution, but under the prior distribution. It is literally the probability for these red or blue data points under this distribution over function values that you see in the background. Here it is. So these terms actually, we can compute these. They exist. But the parameters theta enter in a general, typically nonlinear fashion into this expression. And so therefore, as a function of theta, this is not a simple distribution that we can deal with. There's also a pictorial view on this. If you are thinking of a Gaussian parametric model as some neural network, as I've pointed out before 2 lectures ago, then what we're doing in our setting is we're doing analytic closed form inference on these parameters of the last layer of the network. That's what our Gaussian inference is. And then those parameters depend on, well, they get multiplied with the features of our network. And those features are where all these parameters enter, right? So effectively, when we're fitting these parameters, it's like we're learning the lower layers of our neural network. And actually, that also means that the process we're going to follow will be very similar to deep learning. We'll be doing some kind of optimization, some nonlinear optimization. Maybe gradient descent, maybe something smarter. It's just that in a Gaussian process model, in general, we don't actually have explicit features like this. We just have this joint distribution over function values. So we have to think about something like this, basically. Right? There is this entire function, which we don't know, and that function depends both on the input and those unknown parameters. So what we can do is analytically actually integrate out these function values, and then we're left with a marginal likelihood for theta. And what we're then going to do is, today at least, we're just going to find a mode of this distribution, the maximum likelihood estimate. So if you have a statistics background, we're going to build that maximum likelihood estimate. And maybe you've heard about problems and strengths of maximum likelihood, that it has in some sense some good properties, it's asymptotically efficient and so on, but also some bad properties. It can have a very bad local minimum and so on. We'll discuss this at length in later lectures. Today, we just want to get to an actual prediction. So, okay, what does this explicitly look like for Gaussians? There's maybe one more opportunity to talk about this. So if we find, if our goal is that we want to find the mode of this marginal likelihood, we can think a little bit more about how we actually do this, translate this into our Gaussian code. Right? We have this cool Gaussian.py library. What does this computation actually amount to? Well, what we're going to do is we want to find the maximum of this likelihood, type 2 maximum likelihood. To do that, we are going to maximize this expression that I've just already introduced. So these 2 lines are just basically what I just waved my hand about for. So we're going to maximize the probability for the data under the prior. And the thetas show up potentially in all of these expressions. And now what we can do is we can say, oh, this is a distribution, so it's an exponential of some square form. Well, we're going to find the mode of this. So it might be numerically more convenient to optimize the logarithm of this expression. Why? Because logarithms are monotonic transformations, so they don't change the location of the mode, right? You just rescale everything such in a monotonic fashion so that the highest point is still the highest point. So we'll take the logarithm of this, and actually typically optimizers are designed to find minima, not maxima of some function. So we'll just put a minus in front to make it a minimization problem. And then we can read off what actually the negative logarithm of a Gaussian is. It's this expression. So what is the function we're minimizing? We're minimizing the distance between our data that we observe and the prior mean. Remember, for us in our model, the prior mean is a constant function set to be the data set mean. So we're not optimizing anything about mu. And then there is an inner product of these residuals to the inverse of the kernel Gram matrix, the thing that the covariance described by our kernel function, plus the term that shows up in the log normalizer of a Gaussian distribution. So it's the logarithm of the determinant of this kernel Gram matrix. And this term is, so, okay, maybe let me take 2 minutes to talk about this term in 3 different ways. The first one is, this is a loss function. You've encountered such loss functions in deep learning. You've probably encountered this term. This is an L2 loss. It's just a very like non-standard L2 loss, right? It's a quadratic term in the data scaled by the terms that show up in this matrix. Anyone nod if this is clear to those of you who've done a deep learning course? Yeah, I mean, not for everyone, I guess, right? But yeah. So for those who have this, then there is this extra term here, which shows up because we have integrated out the function values. This is something you wouldn't get in a standard empirical risk minimization setting. You get it only because we've integrated out a Gaussian process distribution. And this term is actually crucial for this to work. Why? Because it captures a measure of the complexity of the model. Determinants of matrices are volume measures. You learned this in your first year linear algebra class, right? Determinants measure the volume of a space. And what these numbers here measure is basically how many different functions your model can fit. So if your model is very constrained, if you can only model very few functions, then this model complexity will be low. And that's a way of building a good model, right? We minimize this expression. We like models that don't have much degrees of freedom. While if the function has function space has a lot of degrees of freedom, this will be a large volume, and we're paying a penalty for this. This is why people have sometimes, in a bit of a PR move, called this the Occam factor, the complexity penalty of the model, due to this, who has heard of William of Occam? See, everyone who's taken a philosophy class at some point, Occam's razor, right? So there's this medieval monk, very little is known about him because he's ancient, right? He lived from 1285 to 1349. Funny tidbit, he was born in the UK, in Occam, that's why he's called William of Occam, which is a tiny little parish town somewhere in England. But he actually died in Munich. This was the Middle Ages, and he traveled around. There is even a street named after him in Munich, the Wilhelm von Ockham or something Straße. And he's being quoted. He's actually a theologian, a monk, and he wrote some theological treatises about basically how to read the Bible, right? And within these, this was sort of Middle Ages philosophy. He made this claim in Latin that is to him, nunquam ponenda est pluralitas sine necessitate. Plurality must never be posited without necessity, or people have reduced this to say you shouldn't make assumptions if you don't need them, right? You should build the simplest possible model for morality, actually, largely for him, but it's also been used in the philosophy of science. What is this thing actually supposed to do? What does this help us with? Well, it's this idea that you should pick models that don't just fit the data well, this is this term, but also models that make as few assumptions as possible. So Bayes' theorem gives us an explicit way of representing this idea by saying when we marginalize out over a function space, we effectively measure the volume of this function space. And if that volume is large, then our distribution will have to put low probability on every single one of these function values. And therefore, we might consider it a worse model than a more compressed model that puts a high probability on only a few predictions. There's also a much less philosophical way of thinking about this that I've tried to show with this plot here. Let's think of the simplest possible case. Let's say I want to learn the scale of a Gaussian scalar distribution. I know what the mean of this distribution is. It's here. And I've made a measurement of one single datum, this red line. And now I want to know what the standard deviation of this distribution probably is. Well, what I do is I just choose particular hypotheses, different Gaussians with different scales. And what you now see is that if I make the Gaussian very narrow, then it can concentrate a lot of mass, but it has to concentrate it around the mean. If I make the Gaussian very wide, then I can incorporate this datum, but I will have to distribute the probability over a larger space. And so after some point, the probability actually goes down for every individual datum. And the point where I just about find the highest possible value for this probability at this point, that's the one over here, that's our maximum likelihood estimate that we are constructing. That's the idea. So it's a very basic idea, actually. It tends to be overloaded with a lot of philosophy. Now, we don't have time to talk about this. If we had more time at some point, I could also talk about how we actually compute this and how we can get gradients about this function. I don't have time to do this, so I'll skip through it. For us, all this fancy mathematics boils down to just one call to our Gaussian library. Why? Because what we're computing here is the prior probability under our Gaussian process prior for the log prior probability for the data that we actually observe at the locations x where we observe it. And we just put a minus in front, and then we have a loss function that we can feed to whatever optimizer we like. And we're just going to do that. So if you found all of this math confusing, you can tell me about it in the feedback. But in terms of computation, it's just a one-liner. You say, here is this object that takes in the parameters of our model, and then it evaluates our data, prior predictive log negative probability, and then we just feed this function into an optimizer. And you could use whichever optimizer you like. You could use stochastic gradient descent, or ADAM, or NADAM-W if you really like. But I'm going to use a more tried and trusted optimization method, because what we're doing here is we're optimizing over something like 12 parameters and a function of which I can readily compute both the gradient and the Hessian. I don't even have to think about how to do this. I just call JAX and tell JAX, just compute the gradient and the Hessian for me, because autodiff is now fine in 2025. Let's please find the best choices. And because I have gradient and Hessian, and the Hessian is not a bad object, right? It's the 12 by 12 matrix. It's not large. I can just feed it into a very powerful optimizer, one that will make use of the Hessian and the gradient. So I've actually done this here. So in this cell, I load from JAX the ability to compute gradients and Hessians. Oh no. Oh, come on. I just really want to show you. OK, so maybe while we're waiting for this, now we're done. Finally. OK, aha, OK. So this optimizer has evaluated the function about 73 times, and it has found a particular value of the log likelihood, which is 217. Minus 217 is the log likelihood. But so that number is not easy to interpret for us, because it's a statement about the probability of 800 data points in an 800-dimensional space. So that density doesn't really mean much, but it is a good choice. Why? Because we can check if we can compare it. I've made a little plotting tool here to the numbers that were found by Carl Rasmussen in his analysis. Now let me see if I can get back to things. So can you read these in the back? All right? So these here are the initial parameters that I chose. You can see that they're quite regular because I chose them to be just some initial guesses. These are the values that the optimizer found. You can check for yourself that they look different from what I initialized them to, and they've changed a bit. These are the values that Carl Rasmussen found, and these are the units of measure of this. And now what you can see, and that was actually my punchline for the end of the day, and now we've just lost the 5 minutes that I wanted to spend on this, is that first of all, you see that these are physically meaningful terms, and you see that in some cases they're quite close to the numbers that Carl Rasmussen found when he did this analysis with the exact same Gaussian process model with slightly different data, slightly older data. And then we find that our model, though, for these long-term parameters, so these are the length scales and the output scale of the long-term model, has found quite different numbers. So this means that our model actually thinks that things are changing on a longer time scale than what Carl thought. And when I first ran this experiment, I can tell you, a few days ago, I saw this number, and I thought the optimizer was not working. I thought, this is not going to be convincing to the people in the lecture hall, because I started with 100, and it just moved to 107. Actually, if you want this optimizer for a shorter amount of time, it only moves to 101. And I'm not like, that's not going to be convincing. It seems like I'm just stuck in a local minimum, and Carl found 66. And then I thought, is it me or is it him who is messing up? Because 66 also sounds like a dangerously smooth number, right? It's 2/3. So when something like this happens, and this can happen, of course, in deep learning as well, right? You look at that number and you don't quite give up yet. So the first thing you do is I make a few samples from this optimized prior. Right? So let me run that cell. This is the kind of samples that this model now produces. Can you see the original data? Raise your hand if you can see the original data. Aha! This is taking a bit longer. So some of you think you can see the data, but it took you some time, right? So I hope you'll agree with me that we now have a better model that describes the data much better. If you remember what the actual numbers are and where we are in 2025, you can actually make out the original data set, but just about. So this model is not so bad, actually, and here is its prediction for the future. The black stuff in the back are prior samples. The red stuff is its prediction. And now on his website, Carl actually says, look at this, we're not doing anything meaningful. It's not getting any better. We can't hope to get the CO2 levels down anytime soon. This is very bad news for humanity. Now, at this point, we can do something like what a good scientist would do is to say, how much do I trust this? And what does this observation about his numbers and our numbers actually tell us? So remember that all of these parameters mean something in our model. They give us an interpretable model. And these two numbers are actually the most important ones in there, because they are the ones that determine how the model is going to extrapolate into the future. How far and how far up and down, right? Over which length scale and over which output range. So it's annoying that those numbers seem to be so different in his model and ours. So what can we do to address that? So here's my final point, and then I'll let you go. Well, we have this loss function that we're optimizing. We have this likelihood. And remember that likelihood is actually a probability distribution over the data. And it's a likelihood function that we could multiply with the prior to get a posterior over the parameters. So we can do sort of the next best thing to Bayesian inference by analyzing the geometry of this likelihood locally. We can't actually compute the posterior because it's too computationally taxing. But we can think about what this negative log likelihood looks like, right? So if you would take negative and then the exponential again, we would get a likelihood. So a way to do that is to compute the Hessian of this loss function at the mode, the curvature at the mode. And I do this here. This is the Hessian of Carl Rasmussen's parameters, and this is the Hessian at the parameters that we found. It's hard to read this, but what you can see is that the first two rows and columns, this is obviously a symmetric matrix because it's a Hessian, the first two rows and columns are white. They have a very low shading, which means that the curvature there is nearly zero. And that's the problem. This model is just not well identified. We don't know what the length scale is, because we don't have enough data yet. We only have 50 years. And so it's hard to figure out whether the length scale is 100 years or 10 years or 50 years. And we can actually turn this curvature into an error bar, and I'll talk more about that on Thursday because I've run out of time, by effectively reading out the numbers from the Hessian, and then we can get a meaningful statement about the parameters of our model that compare to the reference, give us our estimate with an error bar that we can plot to it. And you can see that these error bars are huge for exactly the two numbers that we care about, the predictions into the future. And what does that mean for us? Okay, I'm going to give up now and just show you the final slide and tell you what I wanted to bring across with this punchline. Sometimes it can be that even if you build a very powerful scientific model that builds a perfect, nice interpolation and extrapolates in a very powerful sense into the future, you might still end up being uncertain about the one thing you actually want to predict, what happens next. So when that happens, that's not a negative message for science. It's not a negative message for Bayesian inference or for machine learning. It just means that we're still uncertain. And then the right thing to do is to embrace that uncertainty and say, I don't know, so what do I do with that knowledge that I don't know? Do I say, I don't care, let's keep driving cars and flying planes and burning gas? Or do I say, I actually don't know, but I mean, if you look at this data set, it's certainly not going down anytime soon. I might not know whether it's going down over 50 years or 100 years or 10 years, but it's not going down yet. So we should keep thinking about what to do to get it back down. With that, thanks for your patience while I'm fighting with my code and the Jupyter server in Karlsruhe. I'll come back to some of the questions I had to jump over today on Thursday and use that time to also tell you a bit more about Gaussian process models. Please give feedback.